Okay, so here we have R. R is what we use to represent correlation. Now this is Pearson's correlation, and the R, I don't know why we use R, but we do. So all of this should look familiar. We've done the sum of the differences between the scores before, right? So we've got each score X minus the mean for X. We've only been dealing, when we talked about measures of difference, right? Our difference of means test, we've only dealt with we've dealt with two groups with the same variables. So we're comparing men and women. So it's essentially like that. We're talking about two different groups, right? So we have X minus mean and we have Y minus mean. So we have two variables that we're taking into account. We were talking about two groups before. Now we're talking about two variables. And we have each score minus the mean score squared and each score minus the mean score squared. So a lot of this is going to look familiar. It looks like the standard deviation formula. It looks like the two sample t formula a little bit. We have, we're doing squares, so we're going to be taking square roots. And the formula takes the sum of the product of the deviations from each score, and that's what this is. This is the deviation from each score. We square it, we sum it. Okay, so we're going to be doing that. And then here we have the deviation multiplied by the deviation. And so that's this product of the deviations, and we're going to sum those together. So let's do a calculation example. And we want to look at the relationship between the number of classes taken by a student and the number of nights a student goes out in a week. Now, if we hypothesize about this, we probably think that students who take more classes are going to go out less, right? That would make sense, right? You're going to be too busy. You're going to have more homework. You're going to have a greater workload. So you're probably not going to go out as many times a week socially. So here is our data. We have a student who has 4 classes and they went out 3 nights last week. A person who has 6 classes who went out 2. So these are essentially 1, 2, 3, 4, 5, 6, 7, 8, 9 people's answers to 2 separate questions. Okay, so here we're going back to our hypothesis testing. So we have our step 1, which is our model. We have a random sample. We are doing an interval level of measurement. Okay, our hypotheses, this is like how we worded our hypotheses for correlation, right? So for chi-square, we used words instead of symbols. When we did t-tests and ANOVA, we used symbols for our hypotheses. But when we started talking about measuring association or relationships, we were using sentences to talk about the relationship between the variables. So it's the same kind of thing because correlation is the same kind of statistic. There's a strong relationship between the number of classes and the number of nights out. There's no relationship between the number of classes and the number of nights out. Okay, so our research hypothesis, our null hypothesis, we've done this before. Our significance level, let's just set it at 0.05. It's a nice place to start. Our degrees of freedom, for this is n minus 2. It's the number of respondents, the number of people who answered the question, minus 2. So we had 9 people who answered the survey questions. So 9 is our n, our sample size. Degrees of freedom is n minus 2, which is 7. And our critical value then is 0.6664. Now, just a second. Don't worry. There's a chart. I just haven't shown it to you. Give me a second. I'm also going to post a copy of the chart on Western Online for you to look at. Okay. Correlation is always a two-tailed test. So you see this plus or minus on the screen. That's what that's telling us. It's always a two-tailed test so that we have both a positive and a negative critical value. So we're going to have 2 critical regions. We've done that before. We've done two-tailed tests. We know what 2 critical regions look like. Here is our chart. Now, it may be hard for you to see this depending on the size of your screen, so I am going to blow it up a little bit to show you what it looks like. But essentially, here's our degrees of freedom. This is our alpha. So if we have 0.05 and 0.01, those are the only 2 that are on this chart. You can find charts that go out further than that, and you can find charts that have more detail. So they might have numbers between 25 and 30 and 30 and 35. This one is fine to use, and you can see where I got it from. I got it from a textbook. They got it from somewhere else, so It's totally fine to use this one. You don't have to seek out another one. Also, as we have talked about in other statistics, SPSS will calculate the exact significance level, the exact alpha, the exact P level for your data. And then you have to make a decision of whether that you need to look at that output and determine whether it is statistically significant at the level that you set in the hypothesis testing portion before you run the calculation or before you do the calculation. So in this case, we had 7 degrees of freedom, which gave us 0.664 at the 0.05 level. So that's where that number comes from. So let's do a few examples. We'll come back to our number of nights out and number of classes example, but I want to pop off here for just a second and look at some examples so that we can get more familiar with using the chart. So if we have a degrees of freedom of 18 and an alpha of 0.05, what is our critical value? So what's going to be our critical value cutoff for that? So here's 18. And so 18 degrees of freedom, our critical cutoff is 0.4438. Remember to put the plus or minus there, but we have a critical value of 0.4438. We have a two-tailed test always, so we're going to have one on each side of the curve. So it's going to be plus or minus 0.4438. Let's do another example. What if we have degrees of freedom equals 55 and we want to use an alpha of 0.01? So degrees of freedom of 55 would mean that 57 people answered the question, right? N minus 2 is our degrees of freedom. Well, the closest number that we have is 50. So that's the one that we are going to use. We always play the Price is Right game, right? The closest without going over, and that's based on the limitations of whatever chart we use. So we're always going to use the lowest number, the closest number that isn't above it, because above it is actually going to make it easier to reject our null because we're going from 0.2732 in this case, from 0.3541 to 0.32. So it's easier to get a 0.32 in our calculation than it is to get a 0.35. So we're going to go with the number that gives us the higher threshold. That's the more conservative approach, and that's the way I want you to do it. So our critical value is plus or minus 0.3541. And we use 50 because it is the closest one that is less than our degrees of freedom value. Another example. What is the critical cutoff value for R given degrees of freedom equals 120 and alpha is 0.05? Our chart that we're using only goes up to 90. So that's the value that we're going to use. As I said, other charts expand it further. If you want to use a different chart, just tell me which one you're using so that I don't count your critical value incorrectly, the one that you report to me. But this one is fine to use. So we're going to use 90 in this case, which gives us a critical value of plus or minus 0.2050. Okay, so let's run through the calculation part. Now that we understand where those critical values come from, let's run through the calculation. We already broke down our formula before. Let's run through it and do a practice of how to calculate correlation. What I want you to do is the same thing that you guys did when you were doing standard deviation and chi-square. Because it's a multi-step calculation, create a table, keep it clean and organized, and then you just work your way through the table in the steps of the calculation. So here's the setup for the columns that we need. We need X, Y. We need to do X minus the mean of X. We need that column. We need Y minus the mean of Y column. We need this column squared right here. We need this column squared right here. And we need a column that takes this value and multiplies it by this value. See here? So this part is going to be this column. This one is going to be this column. And this top part here is going to be here. So after we have done all of these pieces, we're going to sum this column and plug it in here. We're going to sum this column, plug it in down here, and we're going to sum this column and plug it into the numerator. That makes sense? All right, here we go. The first thing we have to do is calculate the mean for each of our sides. So the mean for X and the mean for Y. So let's go and do that. So here are our X values. We had 9 of them. So we calculated the mean of X is 4.8. The mean of Y, run through the same process, is 2.6. So now the next thing we're going to do is to take each score of X, take the score and subtract it from the mean that you calculated for group X. So 4 minus 4.8 is negative 0.8. 6 minus 4.8 is 1.2. 5 minus 4.8 is 0.2. And we do the same thing for Y. 3 minus our mean for Y, which was 2.6. 3 minus 2.6 is 0.4. So we're going to do that for both of those. And I've shaded the columns to make it easier as we follow along to know where each piece is coming from. So yellow columns are columns related to X. Blue columns are columns related to Y. And the green columns are when you have X and Y together because green and yellow make blue. Wasn't that fun? Okay. So after we have done our differences here, where we did each score minus the mean and each score minus the mean, we are going to take each of these values and square them. So 0.8 squared, negative 0.8 squared is positive 0.64. 1.2 squared is 1.44. 0.4 squared is 0.16. Negative 0.6 squared is 0.36. Okay, so we're going to square each value for X, and we're going to square each value for Y, excuse me. Then we're going to take our initial difference columns. Don't come over here and grab these. Don't grab our original X and Y. This original deviation columns, and we're going to multiply them together. So 0.8 times 0.4 equals 0.32. And we're going to do that for each. 1.2 times negative 0.6 is equal to 0.72. So that's where this column comes from. Now, let's look at the formula again. This essentially means the sum of the far right column divided by the square root of the sum of the second light yellow column and the sum of the second light blue column, right? So we're going to grab those. We're going to sum this column here, this column here, this column here, and that is going to get plugged into our formula. So we have this column summed together is 12.8. So if you add all these numbers together, you get 12.8. The sum of this column is 18.24, and the sum of this column is negative 3.88. Note that this column is always positive, and this column is always positive. Because we have squared all the numbers, these two columns should always have only positive numbers in them. This one could have negative numbers in them, because if you remember, a positive times a negative is a negative, and a negative times a negative is a positive. So some of those signs will go away and turn positive, but some of them won't. And so you're going to go up on the simple math part of the addition and subtraction here. Plug each of these elements into the formula. So we had negative 3.88 as our numerator, 12.8, and 18.24, and that's under the square root symbol. Why is it under the square root symbol? We squared all those numbers to get rid of the negatives, and we're going to have to undo that squaring to make it something that we can interpret, right? Because we're talking about squared nights out and squared classes. Well, that doesn't make any sense. So negative 3.88, if we multiply these two numbers together, we get 233.47 is equal to negative, and we get a value of negative 0.25. Our decision is going to be to fail to reject the null. And we're going to conclude that there is no statistically significant relationship between the number of classes taken and the number of nights spent out. Maybe that's a little bit surprising. We would expect there to be a relationship, but given our data, given the sample that we have, the relationship was not significant, not statistically significant. So not big enough to be important, if you remember that language from before. Our critical value was 0.6664, and our correlation was 0.25. So that's why it lies outside of the critical region. Remember this chart? So our R was negative 0.25, and our critical cutoff here to put it into the reject region was negative area in the fail to reject region. Same model, same method we were using to calculate all of our other statistics that we applied the hypothesis testing system to. Our interpretation, we are going to talk about how there is a weak negative relationship. 0.25 puts us in the weak region. It had a negative sign, which means it's a negative relationship. Still going to include in our interpretation information about the strength and the direction of the relationship. So we report the strength and direction even or regardless of the statistical significance. It does qualify as weak. That should be noted. Okay.